So this is just a quick recap on all of the grade 11 circle geometry. Pamelo, you didn't get one. Who else did not get? Aha, you were late. The summary of all the grade 11 circle geometry theorems you need to be able to prove for the exam. I'll do that as well. I still have that on my to-do list. Okay, so when you look at the grade 11 circle geometry, we start off by saying a line from the center perpendicular to a chord bisects the chord. Got it. So if I draw a line from the center that is perpendicular to a chord, it bisects the chord. So the way I've set this up is I said, if OC, which is the line from the center, is perpendicular to AB, then the deduction is that AC is equal to CB. Reason, line from center, perpendicular to chord. Then we have the converse of that theorem, which is if a line from the center bisects the chord, so if OC comes from the center of the circle and it bisects the chord, so AC is equal to CB, then that line from the center will be perpendicular to that chord. Those are converse theorems. And you can only use these theorems if I have the center of the circle. If I'm not given the center of the circle, these two theorems do not work. Do you understand? There are certain theorems which, unless the center of the circle is given, it doesn't work. This one, okay, and you'll see the next two theorems as well. If I don't have the center of the circle, the theorems don't work. Now the next one, if I have the diameter of the circle, then please remember the diameter of the circle will always subtend a 90-degree angle on the circumference. And we did revise this one. Remember, we revised this one in the analytical geometry. So one of the questions in analytical geometry was they needed you guys to know that if I draw a right-angled triangle in the Cartesian plane, then the three vertices of that triangle will always be on the circle. Got it? And the hypotenuse will always be the diameter of that circle. So that's actually a very, very useful thing to know. Okay, and the reason, obviously, angles in a semicircle. Next one is the converse of that theorem. I don't know if you were aware of the fact that you do have a converse. As a line that subtends a 90-degree angle on the circumference of a circle will have to be the diameter of that circle. So the moment I have a 90-degree angle anywhere on the circumference of the circle, the line that subtends it is going to be the diameter. Now, a lot of people, I found last year that some people, the reason they struggle with this is because they don't understand the word subtends. Do you all understand the word subtends? Okay. Oliver, subtends. Subtends means that if I take a line and I take the two ends of the line, got it, and then I follow back, that's what subtends means. AC subtends angle ABC. And you'll see the way we write it actually gives it away. Because this angle, when I describe it, what do I call it? I call it angle A to B to C. So because it's angle A to B to C, what subtends it? AC. Angle B is subtended by AC.
So it's where the two lines meet?
It's not really where the two lines meet. It specifically has to do with the fact that the angle comes from those 2 points. Because an angle needs two lines to be created. Do you understand? So the two lines that create the angle comes from the end points of AC. So because the end points from A to angle B and from C to angle B forms line AC, that means AC subtends angle B. Or, if there's no line there, I can say arc AC subtends B. It doesn't have to be a line. The line doesn't have to be drawn. By the way, if there's no line, you can draw it in. That's the nice thing. You can construct a chord. Okay, you can't move the points, but if there's no chord, there's just the arc, you can actually construct the chord just so you can see it a little bit better. Okay, everybody got that? So the way you describe the angle, saying it's from angle A to angle B, no, sorry, from A to B, and B is where the angle is formed, to C. That means AC subtends angle B. Okay, that's what the word subtends means. Then, the reason their chord subtends 90 degrees, which means it's the diameter. Next one, also, you have to have the center of that circle. So this again is one of those subtend. So if you still don't understand that whole idea of subtends, you really need to get a handle on it. Because there's quite a few of these. Angles in the same segment, also, it's about subtending. Tan chord theorem, it's also about subtending. If you don't understand the idea of subtending, you're in trouble. Because then a lot of these theorems make no sense to you. I always say to people, put your fingers on the edges. Follow it, come back, follow it again, come back. So what you want to do is you want to do this. You put your fingers, and this is not a chord, as you can see, this is an arc, but it doesn't matter. It really doesn't matter if there's a chord there or if it's the arc. So I've highlighted that arc, AC. So there's AC. The lines that form angle O go from A to O, and it goes from C to O. So that means angle O is being subtended by AC. Can you guys see that? But in exactly the same way, if I go to angle B on the circumference, then I go from A to B, and I go from C to B to form that angle over there. So the lines that form angle B also go back to that chord, or I should rather say the arc AC. So the arc AC subtends O at the center, the arc AC subtends B on the circumference, so both those angles are subtended by the same arc. Therefore, the angle at the center is twice the angle on the circumference. And that's the theorem. Got it? Angle at center is twice angle at circumference. And I've tried to draw it in a different way because the textbooks normally draw it over here and then they draw it over there. So you can see the arrow. I know Mr. Schofield, I think, calls it the arrow theorem. He's got a couple of interesting names. He calls the tan chord theorem, I think he calls it the windsurfer theorem as well. Okay, if you are with Mr. Schofield, you might have actually, although he didn't teach you guys in grade 11, so you might not have heard it in grade 11 from him, but he does. He refers to it as the arrow theorem, he calls this the arrow theorem, and then the windsurfer theorem. Okay, we're not going to do that. All right, then, next one is just an extension of the previous one, meaning if I again have an arc or a chord that subtends two angles, but now both of those angles are on the circumference, then those angles are all equal. But be careful, people, because a lot of people seem to misunderstand. The arc needs to subtend both angles on the circumference, but on the same side, or in the same segment, I should rather say. Because if this arc subtends that angle over here, but then I had to draw another angle going this way, and a lot of people then go and says, oh, but CD subtends that. No. Minor arc, minor meaning the smaller arc, subtends A. If I were to draw an angle in here, then the major arc, CD, would subtend that angle. You can't have the minor and the major arc. It's both got to be subtended by the minor arc. Do you understand? The smaller one of the two. So that's why angle A goes from A to C, A to D. So that's why CD subtends angle A. But angle B goes from B to C, B to D. So that's why CD also subtends angle B. So those two angles are equal, and the reason, angles in the same segment. Okay, next. This one that I killed you with last year in the final grade 11 exam. That's the one that killed everybody. The very first question said, why are the two angles equal? And nobody could supply the reason except for maybe, I don't know, I think about 15 kids in the whole grade could supply the reason. Guys, this is what we call a corollary. A corollary. Okay, so it's not a formal theorem per se, but it says, if I don't have the same arc subtending two angles, but I have equal arcs or equal chords, meaning AC is the chord that subtends angle B on the circumference, and DE is the chord that subtends angle F on the circumference. Now that's not the same chord, got it, but they are given as equal. So equal chords will subtend equal angles in the same circle. Obviously, can't be two different circles. So equal chords will subtend equal angles on the circumference of the same circle. Everybody understands that? Josh?
And does it work with arcs as well?
Yes, equal arcs. If they give an equal arc, if they say you take this little piece of arc, and that little piece of arc is like 1 centimeter, and then you take another piece of arc, and that piece of arc is 1 centimeter, it works perfectly as well. They generally don't give it with arcs because it's very difficult to give the length of an arc. They generally do it with lines, so it'll be chord, that's a tense. Okay, very important to remember this one. Yes? Yes. Well, you can actually even use the word chord. You can say equal chord because you can draw the chord in, if you think about it. Yes?
I just want to make sure I understand subtended quickly. If I was to look at that, right, the triangle FDE,
Yes.
I could say angle D is subtended by chord FE.
Yes.
So that's correct.
Yes.
I could do the same with angle A is subtended by chord BC.
Yes.
Okay, cool.
But they're not equal. Why? Because FD and BC, you can clearly see, are not equal chords.
No,
Yes.
I just want to check if that's
But
subtended.
yes, that's exactly what subtend means.
Okay, cool.
Yes, 100%. Got it. So equal chords subtend equal angles. Then, cyclic quadrilaterals. Cyclic quadrilaterals, a lot of people seem to complicate cyclic quadrilaterals. People, for something to be a cyclic quadrilateral, it needs 4 points on the circumference of the circle. So they don't actually have to tell you it's a cyclic quad. They just have to tell you that the vertices are located on the circle. So they can actually go and tell you A, B, C, D are on the circumference of the circle. And then that means it's a cyclic quad. Or they could say A, B, B, C, C, D, and A, D are chords of the circle. To be a chord, they must also be on the circumference. So as long as you know those 4 points on the circumference of the circle, automatically it's a cyclic quad. Got it? You don't have to prove that's a cyclic quad, that means it is a cyclic quad. Okay. If the 4 points are not given on the circumference of the circle, then you have to first prove it's a cyclic quad. But if you know the 4 points on the circumference, it's a cyclic quad. Properties of the cyclic quad, 2 properties. The opposite angles are supplementary. They add up to 180, always. And secondly, the exterior angle of a cyclic quad, which means if I extend one of the chords, in this case, I've extended chord DC, and you can call it produced. Sometimes they don't use the word extend, they use the word produced. So they'll say chord DC is produced, and then normally they'll put a point over there. They'll say something like 2 point E. So they'll say chord DC is produced to E. The word produced just means it's a straight line. Got it? That's what the word produced or extend means. It's a straight line. Now, that means you form an exterior angle to the cyclic quad over there. And the exterior angle of the cyclic quad is always equal to the interior opposite angle. So that's why angle A is equal to angle C1, because the exterior angle of the cyclic quad is equal to the interior opposite angle. Those are the 2 properties of the cyclic quad. Okay. Right, next. How to prove something as a cyclic quad. If they ask you to prove something as a cyclic quad, there are 3 converse theorems that you can use to prove something as a cyclic quad. The first converse theorem is just prove that one pair of opposite angles are supplementary. You don't have to prove both pairs, because obviously, if one pair is supplementary, the other pair is automatically supplementary. Okay, and the reason for that, what does the interior angles of any quadrilateral always add up to? 360. So if one pair is 180, then automatically the other pair needs to be 180, because 180 plus 180 is 360. Got it. So you don't have to prove both pairs, only one pair needs to be equal to 180. So those 4 points will not be on the circumference of a circle. So it's not a cyclic quad. But you then just prove either that A plus C is 180 or that B plus D is 180. Then ABCD is a cyclic quad. Why? Because the opposite angles are supplementary. Done. The second one, second converse theorem, is to prove that the exterior angle of the quadrilateral is equal to the interior opposite angle. That's one that a lot of people miss for some strange reason. I find this is the one most people miss when they're trying to prove a cyclic quad. So if I can prove that angle R2 is equal to the interior opposite angle, which is P. So if I can prove R2 and P are equal to each other, then PQRS is a cyclic quad. Why? Reason? Exterior angle is equal to the opposite interior angle. And then, this one is actually the converse of angles in the same segment. The converse of angles in the same segment. If I can prove that there's a line, and again, Oliver, this one's for you. If I can prove there's a line, in this case KL, and that line subtends an angle M over there, and that line subtends an angle N1 over there. Can you see that? So if I can prove KL subtends M2 and KL subtends N1, and I can prove those two angles are equal, then the 4 points are what we call concyclic. They've got to be on the circumference of a circle, and because the 4 points are concyclic, it's got to be a cyclic quadrilateral, because the 4 points are located on the circle circumference. Got it? So you can actually see, there needs to be one line that subtends two angles, but careful, on the same side. The line can't go one way and then go a different way. That can't happen. And that's why the reason there says the line subtends equal angles on the same side. So that's the 3 ways, only 3 ways you can prove something is a cyclic quad. Next. Tangents. Tangents, we have 3 tangent theorems if the tangent is given. The first tangent theorem we revised with analytical geometry. The radius is perpendicular to the tangent. Tangent perpendicular to radius. We did that in the analytical geometry. Second one, we also actually did in the analytical geometry. I showed that to you guys as well. And I even showed to you, if I go and I add the following lines in there, so if I put the center in there, and I draw a line over here, and I draw a line over there, I even showed you, this is then 90 degrees, this is then 90 degrees, and this is then going to be a kite, always, if it comes from the center of the circle. That's also very useful to remember in this case. Okay, but this theorem actually says if I put a point outside a circle, it's got to be outside a circle, and then from that point I draw 2 tangents that touch the circle. Then from the point to the point of contact, and from the point to the other point of contact, will always be equal. Got it? Tangents from the same point. The last property of tangents, or the last theorem that we need to know, is tan chord. Yes?
Just still one of the previous, would our mention would A be, and in the center D, so the thing you drew, yeah, so A, B, O, D, would that be a cyclic quad then?
Yes.
Because it's got 90, 90.
Yes, it's a cyclic quad because it's got 90, 90.
Did I miss that, or was that something that?
No, it's not something I mentioned, but yes, that's a very good observation. Those 4 points will always lead to a cyclic quad because this is 90, so the opposite angles are supplementary. So yes, that's totally a cyclic quad. So not only will that always be a kite, it will always be a cyclic quad. So that's actually also a very useful thing to remember. Okay. Then the next property, or the next theorem, is the one that most of you guys did figure out, just because a lot of people spent time on it, sitting with it and going, I need to figure this out. And this is your tan chord theorem. Tan chord. So I said to my guys last year, when it comes to the tan chord theorem, the important thing here is not the tangent, strangely enough. The important thing here is the chord. Because the angle we are looking at is being formed between a tangent and a chord. Don't focus on the tangent, focus on the chord. So, if I focus on the chord, then angle B3 is being formed by the tangent and chord BD. So again, it has to do with subtending. What is BD subtend? E. So B3 is equal to E. And in exactly the same way, if I look at B1, which is again an angle between a tangent and a chord, do not look at the tangent, look at the chord. What does chord EB subtend? D. So A1 is equal to D. Now, some of you guys messed that up a little bit last year in the exam where it wasn't a chord. Guys, if this is not a chord, say for instance the point ends there and then it goes to the circumference, then you can't use the tan chord theorem because there's no chord subtending the angle. So watch out, it's got to be a chord that subtends the angle for tan chord theorem. Okay. Right, then, last little thing that we need to talk about. There are two ways to prove a line is a tangent to the circle. Two ways. And these are the converse theorems again. So the first converse theorem, if a line is perpendicular to the radius, that's got to be a tangent. Got it? Now careful though, that line can't be a secant or a chord. Do you understand? A secant is a line that will go like this. That's a secant. It cuts the circle in two places. So if I go from the center to a secant, and I prove that this is 90 degrees, that does not make it a tangent because it cuts the circle in two places. Do you understand? Or if it's a chord, that's 90 degrees. It's not a tangent. It's got to be a line, got it? It's got to be a line that is not a chord, not a secant, but it's 90 degrees to the radius, therefore it's a tangent. So that's the first way to prove it. Line perpendicular to radius. The second one, which is the most common way to do it, is to use the converse of the tan chord theorem. And you can actually use the reason there. I know this is a very long reason, but you can use the reason converse tan chord. If the angle between the line and the chord is equal to the angle in the alternate segment, so if those two angles are equal, then according to converse tan chord, that's a tangent. Everybody understands? These are all your grade 11 circle geometry theorems. Okay, so let me pause the video.